get started?
So,
So, the goal of this week is to essentially derive the equations of the universe. It's an ambitious undertaking, but it's one in which we'll see that the equations of the universe we described are applicable essentially from about 10 to the minus 36 seconds to today, and well into the future. So the equations are operative on scales for the universe's homogeneous isotropic. So we have some underlying assumptions here. Based on homogeneity and isotropy, we argued that the natural metric is the Friedman-Robertson-Walker metric. And the Friedman-Robertson-Walker metric looks like a geometry with a line element minus c squared dt squared plus a of t squared, dr squared plus r squared d of a to squared. And this term here is, well, this guy here is for a flat space, but if we consider in more general the flat space, we replace the r squared with s kappa of r squared. So we have here d of negative 2 squared, which is the spherical metric, d theta squared plus sine squared theta, d phi squared. And this new function we introduce, s kappa of r, has various limits. Well, it has various forms depending upon the geometry of spatial slices of space-time. It could be r sine r over r. It could be r, or it could be r sinh r over r. And all of these, when you Taylor expand, have a leading term of r. So, because the universe is very big, you really can't distinguish these three different cases just by inspection. So here, kappa is plus 1, here kappa is 0, and here kappa is minus 1. So kappa is plus 1 corresponds to spherical slices. Kappa equals 0 corresponds to flat slices. And kappa equals minus 1 corresponds to hyperbolic slices. So these look like a sphere, these look like Euclidean space, and these look like a salad. So we have, let's look at this metric. We see there's a parameter, kappa. This is fixed once. So the universe can't evolve from having hyperbolic sections, having spherical sections, or vice versa. We just need to figure out what kappa is, and that's just a parameter in our description of the cosmos. R is the radius of curvature. It essentially tells us either the radius of the sphere or the radius of the saddle. So those are parameters that appear in this metric. In addition to these parameters, we have a function, the scale factor. This is a of t. And figuring out a of t tells us about the dynamics of the expansion of the universe. So the goal of this lecture is to figure out an evolution equation for the scale factor. Okay. This evolution equation turns out to be the Friedman equation. Friedman is the f of the FRW. And in essence, this equation turns out to be one of the components of the Einstein equation. So that's what we're after here. So the goal is to derive this equation today. We'll do a cheat derivation. It's a cheat because you guys don't know general relativity. We'll do a Newtonian derivation of this equation, which gets the form of the equation correct, and there are some factors we need to address. Okay, so it was known as Euclidean geometry was developed that if we just measure a triangle, any triangle, the sum of the angles of the triangle will determine the geometry of the space. So we have an equation like this, and if you just sum the angles on a flat space where kappa is equal to 0, the sum of the angles of the triangle is pi. But if we have a spherical space, the sum of the angles is bigger than pi, and if we have a hyperbolic space, the sum of the angles is less than pi. Now, this extra factor, kappa a over r squared, tells us a deviation. So from being pi. So the problem is that we can't measure directly any more than one angle in a triangle, because these assumptions tell us that homogeneity and isotropy apply on scales bigger than 100 megaparsecs. So if we somehow could build a triangle with side lengths bigger than 100 megaparsecs, we'd be done. We figure out what kappa and r are. But unfortunately, that's not the case. So suppose we've got a positively curved universe. In this case, we can be able to figure out certain things about r without measuring triangles. So suppose you've got a positively curved space, then the Hubble distance is c over h0, and this works out to 4,300 megaparsecs. So suppose you've got a circle, so we'll call this, we've got a circle, the circumference of a circle is 2 pi r, and let's say it's 2 pi r0 today. So in the past, because the universe is expanding, the circle is smaller. So we've got the circle, and it was smaller in the past. You can imagine a light signal propagating around the circle multiple times within the edge of the universe. If that's the case, at multiples of the circumference, we should see the same galaxy over and over again. So if the universe is positively curved, because a positively curved space has compact spatial sections, it's possible to figure out the circumference of the circle by looking at different images of the same galaxy multiple times. Unfortunately, we don't see that. So the universe has a circumference which is greater than the amount of, greater than the distance light can have propagated in the history of the universe, because you don't see different images of the same galaxy over and over again. So in principle, this could have measured positive curvature, but this just tells us that we don't see positive curvature, meaning the universe is old. Okay. Incidentally, if you're short on a mirror, the best way to see the back of your head is to be near a black hole. The light goes around and around the black hole. You can see light from the back of your head very instantaneously because of the strong battery. Same principle. Okay, so let's start thinking about the dynamics of AFT. Now, let's try to derive some aspects of the dynamics. So how does gravity work in Newtonian space, in Newtonian conception of gravity? Essentially, we have the Poisson equation. Poisson equation, which should also be familiar from electricity and magnetism, tells us there's a potential. And this potential, the Laplace unit of the potential, gives us 4 pi g Newton times rho, where here rho is the mass density. So the gravitational potential tells us the acceleration due to gravitation is minus the gradient of this potential phi. Okay, so we have a 1 over r squared force law. So the force due to gravity between two test masses falls off as the inverse square of the distance between the test masses. So So this tells us then, because the acceleration goes like 1 over r squared, the gradient is a gradient of phi, so phi has to go like 1 over r. Okay? You take a derivative with respect to r, you get this 1 over r squared. So we need to use the fact that potential behaves like this in order to deduce properties of behavior of gravity on large scales, which is what the Einstein equation will tell us. Okay, so far we've discussed the Einstein equation only heuristically. So let's make some heuristic observations on the Einstein equation again. So we noticed that the point of the Einstein equation was that it tells matter or energy in space-time how to move, and conversely, the presence of matter or energy deforms space-time and endows it with curvature. So the Einstein equation is a tensor equation which tells us that Gmn is defined as Rmn minus Gmn r. So this is the left-hand side. And this is equal to the right-hand side, which is 8 pi g Newton over c to the 4th Tmn. Okay, so the left-hand side, the important point on the left-hand side is these are geometric quantities. And we can construct this from knowing the line element. These, the right-hand side, are quantities which tell us this tensor here is called the stress energy tensor. Or the energy momentum tensor. And it tells us about the behavior of matter. So this is just at a heuristic level. The important idea is that we're setting geometry equal to the behavior of energy. So what is Tmn? For our purposes, Tmn is a diagonal matrix. The components of this matrix are rho c squared and pressure. So we're working in a four-dimensional space-time. Because working in a four-dimensional space-time, this matrix is 4 by 4. The diagonal entries in this matrix are rho c squared and p. Okay, so the spatial, so the matrix looks like rho c squared, p, p. Okay. Now, let's look at the units here. So we know that E equals mc squared. We can make an energy density out of a mass density by just multiplying by c squared. Okay, so this is energy per unit volume. So we can think about this then as, so this guy here is a mass per volume times the length squared per time squared. Okay, so the units here are mass. So volume is length cubed. You got length squared up here. So 2 of the powers of length squared cancel for the volume. And there's a time squared here. Okay. So pressure is these guys here. So pressure is force per unit area. So this is mass times length squared. Sorry, mass times length per time squared. So it's mass times acceleration. And the area is 1 over length squared. So the units here are mass, length, time squared. So the units of energy density and the units of pressure are the same. So that means this equation makes sense. This equation is basically telling us there's this factor TMN, which appears here. So all the components in TMN have the same units. Okay, so what we've introduced now, using the right-hand side of the equation, is a new parameter, two new parameters if you like, energy density and pressure. So we have some geometric quantity, and this is equal to some energy density. So the geometric quantity is essentially built out of the scale factor A of t. So in addition, we have these parameters, kappa and r. These are just parameters. The only function here is A of t. Okay. On this side, we have two functions now. The energy density as a function of time, and the pressure as a function of time. So there's a mismatch here. We've got two functions on one side and one function on the other side. So it turns out that the resolution to this is that energy density and pressure will be related. They're not independent parameters. And we'll see how they're related as we proceed. Okay, so what we're going to do is we'll do Newtonian derivation. Of the so-called Friedmann equation. And we'll discuss the limitations of this derivation, but I want to emphasize that this is cheating. Okay? But I'll give us more or less the right answer. So we'll start by considering homogeneous sphere of matter. With total mass and sphere. So the total mass and sphere, this guy will be constant in time. And we'll place a test mass at the surface of the sphere. And we'll see what happens in showing you a picture. Okay, so the picture is you have a sphere of radius rs, and this radius can be a function of time, and the force due to gravity is minus g Newton, the mass of the sphere times the mass of the test mass here, divided by rs of t squared. And this is directed in the radial direction. So this is mass times acceleration. So acceleration now, magnitude of the acceleration is going to be the second derivative of the radius. So that's how we've set the problem up. So this guy is minus g Newton, mass of the sphere, divided by rs of t squared. So we want to integrate this expression ultimately. So we'll do this by multiplying both sides by drs dt. This tells us that we have rs dot, the first derivative, drs dt, times rs double dot, and this equals minus g Newton ms over rs squared times rs dot. Okay? So now we'll integrate this. Okay, so what's the integral left-hand side? Yeah. Exactly. So the integral here is 1/2 rs dot squared. Take the derivative, we get 2 canceling, this factor of a half, you have rs dot, rs double dot, which is what we have up here. What's the integral of the right-hand side? Yeah, exactly. So it's G Newton, ms, over rs. And then there's an integration constant. Okay, so this tells us 1/2 rs dot squared minus G Newton, ms over rs equals u, which is constant. Okay, so we'll interpret this as being the kinetic energy. So this is some velocity squared. So this is the kinetic energy per unit mass. And this guy is the gravitational potential energy per unit mass. So what we've written here basically is a statement of the conservation of energy. Okay. So what's ms here? Well, ms is total mass of the sphere, but the radius of the sphere is changing as a function of time. So we can write this as 4/3 pi rs of t cubed, that's the volume, times the mass density, rho s of t. Okay. Then we've used, in our definition of the sphere, homogeneity. Okay? So now we should use isotropy. The expansion of the universe is isotropic. That tells us that rs of t is a co-moving distance, Rs, times A of t. We noticed that in looking at the expansion of the universe, we had some co-moving distance we measured on a grid like this, and this co-moving distance stays the same, but it gets scaled up because of the expansion factor, A of t. Okay. So the isotropy of the expansion tells us the expansion is the same everywhere. There's this co-moving distance Rs, which is scaled up.
So,
Yeah.
is that a times to the minus, and it's supposed to be multiplied out as
It's multiplied. So, given this fact, let's rewrite our expression for conservation of energy. So we have 1/2 Rs squared, A dot squared, and this will equal G Newton over Rs times A times 4/3 pi Rs cubed, A cubed, times rho of t plus u. Okay, so let's simplify this again. This is G Newton, 4/3 pi up here, Rs squared, A squared, rho s of t, plus u. Okay, so the next thing we'll do is we'll divide this equation. We'll divide both sides by Rs squared, A squared over 2. When we do this, we have A dot squared over A squared, and this equals 8 pi G Newton over 3 rho of t plus 2u over Rs squared A squared. Okay? So we knew we wanted to divide by 1/2 Rs squared over A squared. We're going to get rid of this factor of 1/2 and Rs squared up here, and we're going to get rid of this factor of Rs squared and A squared on the right hand side as well. So we simplified things to get rid of that factor. And we notice that A dot over A is h of t squared. So we have an equation for the Hubble parameter as a function of time. Okay? So we only see A dot, the ratio A dot squared over A squared. So a contracting sphere corresponds to A dot less than 0. And these would be describing equations for a collapsing universe. Whereas A dot greater than 0 is an expanding sphere. And this corresponds to our universe, since we observe expansion. Okay.
So,
Yeah.
shouldn't contraction be between 0 and 1?
Shouldn't what be between 0 and 1?
Contracting sphere. Why is it less than 0?
A contracting sphere is a sphere in which the radius is shrinking. So A dot's negative. Since the radius is Rs times A of t. This is decreasing when A dot's negative. Okay, so this is our equation now, and we need to figure out what's u. Okay, so there'll be three cases to consider here. So case one, let's suppose u is positive. So if u is positive, then the right-hand side is always positive. If 8 pi g Newton over 3, those are all positive parameters. We have rho s of t, which is mass density, which is also a positive parameter. And now u is positive. Okay? So this tells us the right-hand side is always positive. So this means a dot squared is always positive. So the interpretation of a dot squared being always positive is the expansion doesn't end. Okay. So if u is positive, we're always expanding. Okay, let's look at case 2. Case 2 is that u is negative. So if u is negative, the right-hand side is 8 pi g Newton over 3 rho s of t plus 2u over rs squared 1 over a squared. Okay, so let's suppose the right-hand side starts out positive. So let's see what happens if this is the case. We can write this right-hand side as 2 g Newton ms over rs cubed a cubed plus 2u over rs squared a squared. All I've done is I've expanded out the rho as a mass over a volume. And let's see when this equals 0. This equals 0 if A achieves a maximum value. This maximum value is minus g Newton m over u rs. Okay, so in this case, the expansion will stop. Will stop with a scale factor A equals A max. Afterwards, this u term will start to dominate this mass term, and the expansion will start to contract. So it'll collapse. So in this case, d squared rs over dt squared equals rs, a double dot, will equal minus g Newton ms over rs squared a squared, which is less than 0. So the sphere will expand to a maximum radius, and then it will collapse. That's what happens if u starts off less than 0. Okay? So we start off with the assumption that the right-hand side starts off positive because we're seeing expansion right now. Okay? So that's what justifies this assumption here. In a different universe, you may see something else. We're not going to worry about a different universe, we're worried about our universe. The right-hand side starts off positive. That's case 2. Case 3 is u equals 0. So u is neither positive nor negative. If u equals 0, this means that a dot will go to 0 as t goes to infinity. And as expansion keeps going, the rho, because the sphere is getting bigger and bigger and bigger, the density is getting to 0 as well. Okay, so I'll let you convince yourself of this. Okay, so there's a useful analogy to looking at all this, and the analogy is, suppose we were to throw a ball at velocity v. If this velocity is larger than the escape velocity, the ball leaves Earth's orbit and it keeps going. So for example, we launched the Voyager space probes at a velocity much bigger than the Earth's velocity, much bigger than the escape velocity of the sun, and these probes are just going. So they'll travel forever. If v is less than the escape velocity, then the ball reaches a maximum height. And then it comes back down. Okay, so that's the second case we studied, where expansion reaches a maximum and then it again collapses. If v is exactly the escape velocity, then the speed of the ball approaches 0 as time goes to infinity. So there's an analogy then between the three cases we looked at and the future of the ball we throw up, depending upon what its velocity is. Okay, so we've derived some equation then that describes the Hubble parameter, the scale factor, as a function of this parameter u that we've introduced. This parameter u should be regarded as analogous to the parameter kappa that we've looked at, describing the different spherical sections of the universe. Okay? Different spatial sections of the universe. Any questions? Okay, so we've done the derivation. What's wrong with this derivation we've done? Well, a lot of things. So let's discuss all the things that are wrong with this and why we shouldn't trust this, even though it more or less gives us the right answer. Okay, So let's list the reasons to be suspicious. Okay, first reason. A spherical volume of finite radius, Rs, is not a homogeneous isotopic universe. Okay, so suppose you've got a spherical volume, and suppose you have another spherical volume of a bigger radius. So you can check for yourselves that most of the volume is close to the surface. Okay? So because most of the volume is close to the surface, most of the mass is close to the surface. Since mass density is given by the mass times the volume. So as a result, this universe is definitely not homogeneous. There's a difference between being here and being here. It's also not isotropic because there's a preferred direction towards the center. Okay? So this means the assumption we've used isn't the assumption that we want to describe a homogeneous isotropic universe because we're not working in this context. So there's special points, the center of the sphere. There's a special direction towards the center of the sphere. Okay, so that violates homogeneous isotopic. Yeah.
What do you mean amongst the masses at the surface?
Okay, so you consider the so suppose you look at the volume. You have 4/3 pi Rs plus delta Rs cubed, and you compare it to 4/3 pi Rs cubed. Okay, so if you take the limit where Rs is large, and you look at this ratio between the volume in this shell compared to the volume of what's below the shell, this has a non-trivial ratio. Okay. So this is especially pronounced in higher dimensions. So the higher dimension of the sphere you have, the more it's the case that the volume is localized in the surface of the sphere. So, for example, if you're doing statistical physics and you're looking at Fermi levels, you'll find that the Fermi C has density close to the surface of the Fermi surface. Okay. The second point is that suppose you've got a spherical shell. In a spherical shell of matter, say, what's the acceleration within the shell? 0. So this tells us that some mass is not accelerated by stuff at radius r bigger than Rs. So that's just kind of weird. So this is a problem if we regard the sphere we're looking at as a sphere that's cut out of the universe as a whole in constructing these equations. Okay? So the entire structure of this derivation just doesn't make sense physically. At the same time, the equation we derived is essentially correct. Okay, so this is a case where very bad approximations give us the right physics. If we were to do a proper derivation, the equation we'll find is the one I'll quote, how does this equation will actually work? So we derived the equation that our derivation gave us a dot squared over a squared is 8 pi g Newton over 3 rho of t plus 2u over rs squared a squared. The equation that we actually want, the Einstein equation, Friedmann equation, is a dot squared over a squared is 8 pi g Newton over 3 c squared epsilon of t minus kappa c squared over r squared 1 over a of t squared. Okay. So here, rho c squared is epsilon. So we can just substitute epsilon over c squared for rho. The same, so the first part of the equation is the same. And then instead of 2u over rs squared a squared, we replace the coefficient with kappa c squared over r squared, and we keep the 1 over a squared in the denominator. So we're very close. Okay, so next time we'll discuss a bit more about what this means. Any questions? Okay, so I think Thursday is a holiday, so I'll see you on Friday.